Subscribe to our YouTube channel and press the bell icon to get the latest updates.
January the 4th is Isaac Newton's birthday from the year 1643, and Newton gave us the gift of Newtonian physics, which were some of the earliest laws that described how the world around us worked and how objects around us moved. Physics has of course evolved since, and today we have the wonderful theory of general relativity, from which we're still learning new things about our universe. In this video, let's take a very basic, simplified look at the laws Newton put forth, where and why they don't apply, how relativity helped solve some questions, and where Newton and Einstein differed in their theories. I'm Sandhya Ramesh, and this is Pure Science. In the 17th century, Newton came up with a set of rules and equations that describe the physical world around us. We all know these if we've studied Newton's 3 laws of motion in school. The first law, the law of inertia, states that a body at rest or in motion will continue to remain at rest or in motion unless an external force acts upon it. The second law states that the force acting on an object is the product of its mass and acceleration, F is equal to ma. The third law is that for every action there is an equal and opposite reaction. Newton also gave us the famous law of universal gravitation. The force of gravity between two objects is directly proportional to the product of their masses and inversely proportional to the square of distance between them. All these equations and laws are a part of Newtonian mechanics or classical mechanics. These laws and equations came with an important property, which is that all observers, no matter where they're situated and whether they're moving, that is, regardless of which inertial frame they are in, they would see the same things around them happening in the same way. These laws were considered to be universal. An inertial frame of reference is our way of understanding and describing relative motion. Say a person is walking in front of me from left to right. I am stationary, so the person appears to move to me and is, of course, in fact moving. However, both of us are on the surface of the earth and the earth is revolving around the sun, moving through space. But for the purposes of this observation, we assume that the earth is stationary. So earth is our inertial frame of reference. We've seen more examples in our school textbooks. If a person traveling in a train throws a ball up and the ball falls down, it will fall straight down for the person inside the train. But if I'm standing on a road and seeing the train pass by, I would see the same ball taking a path that is parabolic. For the person inside the train is the inertial frame of reference and the ball is moving relative to the train. Inertial frames are in inertia, so either in motion with the same velocity or at rest. They are not accelerating. Then, in the 19th century, James Clerk Maxwell came up with a set of equations when he was studying electricity, magnetism, and light. This was combined to form what we know as electromagnetism today. But a funny thing about these equations were that the form of these equations changed depending on the observer's inertial frame of reference. Then came along Hendrik Lorentz in the early 20th century, who, with what we know as Lorentz transformation, which we're not going to go into, was able to show that these equations could have their form preserved even when the inertial frame changes. The Lorentz transformation of inertial frames, was different from the standard transformation of inertial frames that was being applied for Newtonian physics. In Newtonian physics, length and time are constant, they are absolute and don't change. So an object of a certain length in one frame is of the same length in a different frame as well. And this is the same with time. It passes the same way in all frames of reference. But the Lorentz transformation showed that time and length actually do change depending on which frame of reference you're in. And this made who else but Einstein think. He wanted to understand if time and length, by length, space, were invariable. So he first came up with special relativity in 1905. This theory postulated that the laws of physics are absolute in all inertial frames of reference, and that the speed of light in vacuum is the same for all observers, irrespective of whether the observer or the source of light is in motion. But without going into too much details here, Einstein basically realized that gravity changed everything. This was because gravity was basically acceleration. For Earth, we know the value of small g, 9.8 meters per second square, which means that any body that is falling towards the surface of Earth is accelerating or increasing in speed at the rate of 9.8 meters per second every second. The falling object would experience the same force if it's inside a vehicle that is accelerating at this rate or at 1g. And when acceleration or gravity was factored into these equations, even basic geometry changes. This led Einstein to realize that gravity was actually the result of motion, not just through space, but also through time. All of this is, of course, extreme simplification of all the work that went into it, but Einstein then eventually put forth his theory of general relativity in 1915 with the premise that mass distorts and bends space-time, causing it to curve, and gravity is essentially the result of motion in this curved space-time. Now, where do Newtonian physics and relativity differ? Technically, they don't contradict each other, but when energies or velocities are approaching the speed of light, relativity applies instead of Newtonian physics because of space-time curvature. In Newtonian physics, there is no difference in space and time no matter where you're located or how fast you're moving. In fact, theoretically, you can travel as fast as you want if you have enough force. Relativity, however, states that nothing can travel faster than the speed of light. General relativity changed the field of physics completely. It entirely transformed how we understood the world around us and the universe around us. It offered explanations for many lingering questions in physics and in astronomy, such as, very famously, the example of the orbit of Mercury. With Newton's laws, in a two-body system such as the Sun and Mercury, where one object is orbiting around another, the orbit will be in the form of an ellipse with the bigger mass at one of the two focal points. This is true. We do know that pretty much all orbits are elliptical to varying degrees. So it was thought that in this classical elliptical orbit, according to Newtonian physics, that Mercury was in, the perihelion, or the closest point to the Sun in the orbit, was fixed with every orbit, and the data and observations fit this theory. Determining the orbit of Mercury was one of the biggest tests for general relativity. But of course, just like Newtonian physics couldn't answer everything that we observe around us, general relativity doesn't either. Black holes are predicted by general relativity, and singularities, where all known laws of physics break down, are allowed in general relativity. But at the point of a singularity inside a black hole, the laws of relativity also break down. Similarly, we have many other questions from general relativity that are still unanswered, which hopefully in the near or far future we are able to answer, because time flows in only one direction.